Hi everyone, let's continue. Electric conductivity. Electric conductivity materials are divided to three main parts, divided according to their ability to conduct electricity into first insulator, conductor, and semiconductors. Maybe you remind what's meaning insulator, what is meaning conductor, and what is meaning semiconductor. Let's explain. Insulator materials in which the electrons are closely connected to the nuclei of their atoms and cannot move freely within the material. Examples of insulating materials, for example, rubber, glass, mica, dry silk, distilled water, and other materials. These materials they are not transferring any electrics and any heat. Secondly, conducting material transferring the electric through it means it allows electric charge to pass through it immediately, and metal are considered that conduct electricity, and the best one is silver, allowed by copper and aluminum. Last one is semiconductors are those materials that have intermediate properties between conductor and insulator in terms of their ability to conduct electrics, and the most common is the silicon and germanium. Let's watch the video.
Electrical conductivity. Electrical conductivity is a measure of how well a material accommodates the movement of an electric charge. Its SI derived unit is the Siemens per meter. The materials which allow electric current to pass through them are good conductors of electricity. On the other hand, materials which do not allow electric current to pass through them easily are poor conductors of electricity. You know that metals such as copper and aluminium conduct electricity, whereas materials such as rubber, plastic, and wood do not conduct electricity. Good conductors have higher electrical conductivity than insulators.
Electric charge density. The amount of electric charge per unit area of the charge isolated conductor surface, and the charge density of the spherical mineral surface is calculated as following. Then charge density equals the amount of charge on the conductor's surface over surface area for the conductors, or we can show the symbol density and charge and area, or shortly we can show look like this. Each charge density we can show Latin letter called sigma, measured by coulomb over meter square. Q amount of charge measured by coulomb, the unit. A surface area for spherical charge isolated conductor and measuring by meter square. The electric field. The electric field of an electric charge is the space around the electric charge where the effect of an electric force shown on a positive test charge placed at any point in the field. For example, it is each line is showing the electrical field area. But its direction is important. For example, This is positive, this is negative electrical charge. Positive when it's made by a positive charge and the field is negative. If it's made by a negative charge, an electric field is represented by lines called electric force line or the electric field line. And the electric field line is the path taken by a free positive test charge when placed in the field. And electric field lines are characterized by, firstly, it's generated from the positive charge and perpendicularly over the charged surface, and it's directed toward the negative charge perpendicularly over the charged surface by the negative charge. Let's look at the figure. Look at this. Direction is from positive to negative. Secondly, the tangential of the force line at any point represents the direction of the electrical field at that point. The figure, look at this, positive, positive. Look at this, both of them they are repel each other. Electric field for two same charge, they are attract, or electrical field for two different charge, they are attract each other. The line is passing the one charge to another charge. Third one is electrical field line don't intersect with each other but they repel and tension to take the shorter possible length, and we can definition of the electrical field quantity at any point as the amount of electric force that the field effect on a charge placed at that point divided by that charge quantity. Look at the figure. For example, this one is iron pieces. When we are giving the electric, they are moving the another side, and it is moving the positive to negative quantity charge. Electrical field, we can using one equation. Electrical field equals electrical force over charge affected by the field, or E is the electrical field measured by, or the unit of electrical field, Newton over Coulomb. Or we can show the symbol E equals F over Q. F affecting force measured by Newton, Q charge that affected by the field measured by Coulomb, and have the microcoulomb and picocoulomb part. Do you remember micro and pica? And when the electrical field is generated by a point charge, then the affecting force F on the test charge Q is given following the relation Coulomb laws equals, you remember, F equals K constant number multiply Q1 multiply Q2, or testing Q over R square, or distance square. And since the electrical field F over Q, or Q is meaning testing electrical charge, E is electrical field generated by the point charge at distance R from it, Q the point charge which causes the electrical field, R the distance between the point and the point charge, K the constant number 9.10 power 9 Newton multiply meter square over Coulomb square. And homogeneous and non-homogeneous. Homogeneous, all of them is same or two or more levels. Homogeneous electrical field is the field that has constant amount and direction at every point of its points, and the electrical force line in it are parallel and of constant density and homogeneous. Electrical field can be made by charging two white parallel plates with the two equal and opposite charges, and the electrical field lines in the area between the two plates and the distance between them is equals parallel two plate, positive charge and negative charge. Negative effect of bending edge, and that means the field have same amount and same direction at all points. Non-homogeneous electric field, the field that's amount charge from a point to another, like the field generated from a point charge or around a charged spherical conductor, where the field decreases as we get far from it due to decrease in the density of electric charge lines. Look at this. Positive charge. Example. Two identical parallel plates are charged with two charges of same amount and different type. A charge of 2 multiplied 10 power negative 6 coulomb at point A. See the figure? Between the plates, and it was affected by an electric force of 6 multiplied 10 power negative 4 Newton in the direction of the field lines. A. What is the type of the point charge? Firstly. Secondly, calculate the amount of the electric field at point A. Third one is, if the charge was moved at point B, what is the amount of the affecting force on it? Now it is given, it is giving the Q, it is electric charge and force, electrical force, and they are asking the electrical field. Also, our equation is E equals force over Q. First one. Force is the direction electrical of the field, then the point charge is positive. Look at this. Objects moving the positive to negatives. Its meaning force is the direction of the field than the point charge. Is positive. Second, E equals, we are using our equation F over Q. F equals 6 multiplied 10 power minus 4 over 2 multiplied 10 power negative 6 equals 3 multiply 10 power 2 Newton over Coulomb, or 300 Newton over Coulomb. 3. If the charge was moved at point 1, point B, what is the amount of affecting force on it? Charge moved to point B, point B will affecting by the same amount of force. It's meaning 6 multiplied 10 power negative 4 Newton in the direction of the electrical field. Let's continue. Example 2. And we have the one spherical object. A charged spherical conductor of 100 picocoulomb. Pica, do you remember? First chapter. Pica affecting 10 power negative 12. Pica equals 10 power negative 12. Charge and 1 centimeter radius will calculate the electrical field at the point that 50 centimeter from its center. Second, the electrical field on the surface and the electrical field at a point inside the sphere. Let's continue. We are writing our equations. Do you remember our equations? E equals K multiply Q over, do you remember, R squared equals K, it is given 9 multiply 10 power 9 multiply Q 1 picocoulomb, pica 10 power minus 10 minus 12, 100 multiply 10 power negative 12 over R equals 0.5 meter, 50 centimeter equals 0.5 meter square equals or equals 3.6 Newton over coulomb. Second, the electrical field on the surface. It's meaning we are using 1.5. 1 centimeter equals 0.01 meter. We are using our same equations. E equals 9 multiplied 10 power 9 multiply charge is same 100 multiplied 10 power negative 12 over R square, R meanings 0.01 square equals 9,000 Newton over coulomb. And third one is 3. The electrical field at a point inside the sphere. The electrical field inside the conducting sphere equals to 0, since there is no charge. there is no charges, or E equals 0.